All right, today we're going to get started. My apologies. I won't have my camera today, but it should be fine to go over the content without needing it. So let's go ahead and have a word of prayer as we get started with chapter 5. Dear Heavenly Father, Lord, thank you so much for today. I ask that you please be with us as I cover the next chapter. Help everyone to understand the information. In Jesus' name I pray, amen. All right, so chapter 5 is talking about the stereochemistry of tetrahedral centers. All right, so we're looking at carbons that are bonded to 4 different things, 4 different single bonds, and that's going to be on chapter 5. And so these are our objectives that we're going to start off with for today as we move forward. All right, so stereochemistry. What exactly is stereochemistry? Stereochemistry is the arrangement of atoms in a 3D space. And so you're actually seeing the orientation of the individual atoms. So like if we look here at the first example, we see that, we see that the hydrogens here are ones going in front and then the other one's going behind. And then we have our X, which represents usually halogens. That is going to be in plane with the other hydrogen here. Whereas we can see that once we attach another substituent onto the carbon in the form of Y, we're able to actually see the 3D space that it's occupying. So why is this important? Well, enantiomers are types of isomers where molecules that are not the same as their mirror images. Okay, these are when you have molecules that are not the same as their mirror images. And so this is a result when tetrahedron bonding to 4 different substituents forming a chiral center. So let's look at the bottom example here. We see that the carbon here is bonded to X, Y, and Z. And then we have a hydrogen over here. Notice that when they're bonded to 4 different things, the mirror image is not superimposable onto the original molecule. And we're going to see that in real life time in a second. However, if you're bonded to just 2 different things, as in the first one, they are superimposable. They can connect on top of each other. If you're bonded to 3 different things, but you have something that's the same, those are also not enantiomers because they don't have what we call chiral centers, and we'll talk about that more. But when you have chiral centers, is when your carbon is bonded to 4 different things. So what's a chiral center? A chiral center is a result of carbon being bonded to 4 different things. All right, so now let's look at this here. If we're looking into the molecules, this point in a molecule where 4 different groups are attached to a carbon is the cause of chirality. So let's look at this here. The star carbon in the middle, it is bonded to a bromine, a hydrogen, and then on this side you have a 4 carbon chain, and on this side you have 5 carbon chain. Because this carbon does not have any symmetry, we will consider that chiral. Let's continue to look at this. 2-methyl-cyclohexanone does not have a symmetrical plane. All right, so let's look at the 2-methyl-cyclohexanone that's on the right. If you notice, if I go here in the middle, there's no line of symmetry, okay? If I go here, there's no line of symmetry. Here, no line of symmetry. There's absolutely no line of symmetry. Since there's no line of symmetry, this compound is considered to be chiral. Okay? It is considered to be chiral. And as a matter of fact, here you actually have a chiral center because that carbon is bonded to a methyl group, a hydrogen group. If you go here, you have a CH2. And then if you go here, you have a ketone. And so that carbon here is what we call chiral. Now, if we look at the other compound, we have what we call achiral. There is a symmetry line or plane. There's plane of symmetry. We have sides that are going to be the same. Okay? And so because of that, this carbon here is achiral. It's not a chiral center. There's no chiral centers. If there are no chiral centers, the molecule will be achiral. All right, so let's see if we can identify the chiral centers in this compound. So what I'm going to do is I'm going to label them A, B, I'm gonna call this one B, call this one C, and this one D. Let's talk about A first. Is A chiral or achiral? Or well, I should ask, is A a chiral center? Let's say it that way. All right, so if you notice with A, this carbon here is bonded to a hydrogen, a methyl group. If I go this way, I get to a CH2. And then if I keep going, I get to another CH2. If I go this way, I do get to a CH2. So far it is the same. However, if I go again, I get to a carbon that has an OH group. That is not identical to the other side. So if I put a line here, there's no line of symmetry. This is different from this. Okay? So therefore, A is bonded to 4 different things. So A would be chiral. Now, if we look at B, we know we have 2 hydrogens on B. And so because we have 2 hydrogens on B, there are already 2 identical substituents. Therefore, B cannot be chiral. Now let's look at C. Is there a line of symmetry if I draw a line through C? No. You have a isopropyl group here. You have a hydrogen, so that's 2 different things. If I go this way versus going this way, they are not identical. Therefore, C is chiral. And then if we look at D, for the very reasons, I have a hydroxyl group, a hydrogen, so those are not identical. And if I go this way, I get to a CH2. If I go this way, I get to a carbon with 1 hydrogen with some other things attached to it, so they're not symmetrical. No line of symmetry. Therefore, A, C, and D are all chiral centers. And here you see them all highlighted. And this is the compound for menthol. All right, so what I want you guys to do for A is identify the chiral centers. If you identify this center right here, that indeed is chiral because it's bonded to a methyl group, a bromine. You do have a hydrogen that's also here. And then you have this isopropyl group here. 4 different things are attached to that. Very good. Now, I want you guys to work on B, C, E, F, G, and H on your own time as examples. But let's look at D real quick for an example. Where would our chiral centers be? All right. So if you have a CH2, automatically where those are, we know that they're not chiral centers. because you have two hydrogens. If you have a CH3, we also know that those are not chiral centers. So what you're going to look at, you're going to look at the carbons that have only one hydrogen to see if they're bonded to four different things, making them chiral centers. And so we have a CH here with only one thing, and it's a methyl group attached to it. We have a hydrogen attached to it. And then if you go around here and here, there's no symmetry. And so with that, we know that this indeed is a chiral center. Now let's look at this one. We have an OH group attached to it, as well as a hydrogen. And if I go around the ring, we see that there is no line of symmetry here. Therefore, yes, indeed, this right here, the carbon here, is definitely a chiral center. Now, if we go here, we do have an isopropyl group. We have a hydrogen that's understood. And if you go around the ring, again, there is no line of symmetry because this OH group is not here. And so there's no line of symmetry. Therefore, indeed, this also is chiral. Now we have a last CH group here. However, this CH group here has two methyl groups. Those are identical. Therefore, you have something that is the same, so that one would not be chiral. All right, so our chiral centers would be here, here, and here. And again, for A, chiral center is here. So I want you guys to take some time to see, can we find, let's see, what can we do? Let's look at B. Let's do one more. Let's look at B. I'm going to give you guys some time to figure out what the chiral center for B is. So again, if it's a CH3 or a CH2 carbon, those are not going to be chiral. So let's highlight those. I'll give you a chance to figure them out. All right, so it should be obvious. This is a CH2. This is a CH3. This is a CH3. Now for our CH2s, we have a CH2 here. This also is a carbon with a CH2. So there's only one green light that we have here, which this right here is a CH. That CH is bonded to a methyl group. If I go here, I have an ethyl group. Of course, you have the hydrogen there, that's different. And then if I go this way, I have a CH2, but I also have an OH group here. That is not identical to any of the other sides. Therefore, if I draw here, there is no line of symmetry. Therefore, this is definitely a chiral center right here. All right, so when you're dealing with chiral centers and enantiomers, we have what we call handedness of life. So the questions we ask is, why can't you put your right shoe on your left foot? Why can't you put your right glove on your left hand? The answer is because of a condition called handedness, which prevents the right sense object fitting a left sense object. An object that has left and right sense handedness forms a said to be chiral. Okay, so if they are mirror images of themselves, okay, these would be said that they are chiral. And they're even more specifically, they are enantiomers of itself. So stop right now. Try to put your right hand and your left hand on top of each other with both palms facing up. If you have both palms facing up and they're pointing in the same direction, notice that your thumbs do not overlap on top of each other. It takes them to be mirror images of yourselves with one palm touching the other palm for your thumbs to be on top of each other. This is handedness. When you have something pointing in the same direction, but they are not identical, as your hands and your palms being both pointed up, not being identical, with your thumbs not overlapping. Here you can see that chiral objects have mirror images that are not superimposable. So again, they're mirror images of themselves, but they are not superimposable. Your thumbs do not match up when your hands are pointed in the same direction. Whereas achiral objects have mirror images that are superimposable. So yes, there are mirror images, but we can overlap them. And when they're overlapped, they are identical. So let's look at these objects and figure out which ones are chiral. Now, some of them might trick you because you don't realize that they are actually chiral centers. Let's look at the screw. Screws, believe it or not, even though they look like they're achiral and they are superimposable of each other, if you look at the direction of where the threads, you will notice that they do not overlap on top of each other. They have handedness. Let's now look at the shell. The shells, when they're pointed in the same direction, they have mirror images, but are they superimposable? No, they are not. This side of the shell, when put over this side of the shell, they do not line up. This shell would have to flip on top of the shell for them to line up. Therefore, they are not superimposable. Now let's look at the car. The car indeed has a line of symmetry. Due to the line of symmetry, not only do they have mirror images of themselves, but they are indeed superimposable. Therefore, these would be achiral. Nails also, because they're just straight down and there is definitely a line of symmetry here, these two would be achiral. Now, as far as this basketball goes, if you're looking at it, again, it has a mirror images of themselves. And if you overlap them, do you have a line of symmetry? Yes, you do. Therefore, this ball is also achiral. Oops, excuse me. All right, so how to test for chirality in molecules? Well, stereoisomers that are not superimposable with their mirror images are called enantiomers. So again, if you have a chiral center and it's not superimposable with each other, the type of isomers that they are, the type of stereoisomers that they are to be specific, are called enantiomers. Test for chirality. What you're going to do is first look for a carbon that is bonded to 4 different groups. Okay, so first of all, it has to be a tetrahedron center. So the carbon cannot have any double bonds or triple bonds. It has to have only single bonds attached to it. Okay, and so once you figure out that the carbon has 4 things attached to them, they have to be 4 different things. So again, they can't be a CH3, they cannot be a CH2 bonded to 2 other things. It has to be 4 different things. Once you've noticed that there's 4 different things, the second thing you're going to do is look for a plane of symmetry. If there is no plane of symmetry, then the molecule indeed is chiral. So let's look at lactic acid. The carbon here in the center is definitely bonded to 4 different things. You have a hydrogen, you have a carboxylic acid, you have a hydroxyl group, and you have a methyl group. So you have H, X, Y, and Z. Now, if you look at lactic acid, you can have 2 different versions of it, okay? And so if you notice that these are mirror images of each other, and so lactic acid here is the enantiomer of the lactic acid here. And you notice that the names are changed to show 100% inversion. All right, so let's do again. Let's do another test. Let's look at propanoic acid. If you look here, this carbon has 2 hydrogens on the side. So this carbon is not bonded to 4 different things, only hydrogens And then you have something different here and something different here. But it is not 4 different things. Therefore, there's a line of symmetry. This is an achiral. Whereas with lactic acid, we're bonded to 4 different things. OH, methyl, carboxylic acid, and a hydrogen. There's no symmetry in the plane. Therefore, it is chiral. Again, we're looking at the examples before. If you go through this methyl group here and you look at both sides, it's symmetrical. However, if I go through here and I look at both sides, they are not symmetrical. One side has a ketone where the other side does not. All right, let's draw mirror images of this compound. So if you're drawing a mirror image, you would start with what is in the plane. It's going up, and then this chlorine's going back, so it'd be going back here. CH3, bromine. Okay. These are mirror images. Notice that they are not superimposed with each other. It's bonded to 4 different things, so these would be chiral. And a matter of fact, these 2 are enantiomers. The same if we draw the mirror image of this. Chlorine, hydrogen here, bromine here. They're bonded to 4 different things. These indeed are chiral. So I want you guys to do some practice here. So I want you guys to draw 2-fluoropropane. And while you're not going to bring it to next class because we're virtual, I'm going to let you guys answer it right now. 2-fluoropropane, is that chiral or achiral? All right, now let's try 3-methylpentane. Is that chiral or achiral? Now, we already did cycloalkanes, and so I'm going to let you guys do those examples as well. It's cis-1,2-dichlorocyclopropane. Let's see if you can draw that. Is that chiral or achiral? Now, for the sake of assisting you guys, I'm going to draw the last one, trans-1,2-dichlorocyclopropane, to make sure you guys know how to do that. So we're going to draw our cyclopropane. And then on the 1 and 2, we have a dichloro, and they're trans. Therefore, one's going to go in the front, and one's going to go in the back. Is there a line of symmetry? Well, if I draw a line this way, one's going back and one's going up. Therefore, there's no line of symmetry, so this would be considered chiral. Now let's go back and you do the other ones. Dichlorocyclopropane again, but this time they're cis to each other. If I draw my line of symmetry, they're both on the same side. They're both looking, they're still symmetrical. Therefore, these would be achiral. And I skipped over this one, so let me go ahead and do this one. It is 1-chloro, 2-methyl, butane. And so with this compound here, I do not see a line of symmetry. There's no line of symmetry. Okay. Indeed, this carbon here is a chiral center. It's bonded to a CH3. This bonded to a CH2 with a chlorine on it, or a CH2 and a CH3 on the other side. And of course, you have a hydrogen. It's bonded to 4 different things. Therefore, it is chiral. So why is studying this topic of stereochemistry so important? Why is it so important? Well, stereoisomers are readily distinguished by chiral receptors and enzyme activity sites in nature. Properties of drugs depend on the stereochemistry. So let me show you how important it is. If you notice, looking at A and B, if you have a receptor that has to attach to your substrate, the stereochemistry of the substrate matters. Carbon is bonded to 4 of the same different things, but they're 4 different things nonetheless. Okay, so again, I'll say that carbon is bonded to 4 different things. Now, while the 4 different things are the same 4 different things, they are arranged differently in the 3-dimensional geometry of it. Therefore, A fits perfectly into the receptor, where the enantiomer B does not. It cannot fit. And since it cannot fit, you're not going to have binding. This is very important, dealing with nature and drugs. Here's a story which talks about the importance and kind of how the topic of stereochemistry became so important. Thalidomide was used in Britain from 1959 to 1962 to treat morning sickness of pregnant women. It has a single stereogenic center. Therefore, it is a chiral and has a mirror image that is not superimposable. So again, because of the chiral center that it has, which is right here, they are not superimposable. They are enantiomers. However, in the drug in 1959 to 1962, both stereoisomers were present in a single dosage. Because of how it was synthesized, they didn't isolate the two. They didn't realize it was so important. So you had what we call R-thalidomide, and I'll explain what the R means, and you had S-thalidomide. Well, the sad truth is, while one allowed for, while one allowed for women to be treated for morning sickness, the other ones caused their babies to be terminated. And so it was causing birth defects as well as miscarriages in women. And so this just shows you the importance of stereochemistry and when it comes to studying it and identifying it in reference to drugs. So now, what does this R and S mean? Well, R and S is a way to be able to use nomenclature to distinguish the difference of the various stereoisomers. All right, so again, bonded to 4 of the same things, but the orientation would be different. So stereoisomers or enantiomers they're always come in pairs, okay? They, again, always come in pairs. So you have an R version and an S version. And so let's talk about the system of how we do that. When you're dealing with an S version, that is when you designate your substituents using numbers, okay? You designate your substituents using numbers. So you number them 1 through 4 using a system that we're going to talk about. Once you number them 1 through 4, you make sure 4 is in the back. You see how there's wedges, so 4 is in the back. And then if you go counterclockwise, or we say left, we say sleft. So if it turns left, going this way, 1, 2, 3, we say that S for sleft. So 1, 2, 3, go in that order, sleft. Now, if you're going 1, 2, 3. Again, R always having to be in the back. And you're going clockwise. That is going right for R. So R for right, S for left. Now notice that 4 has to be in the back. Let's go a little bit deeper in this. So when you're doing the system, the first thing you need to do is know how to assign priority, 1 being the highest and 4 the lowest, based on atomic numbers of the 4 groups bonded to the tetrahedral center. If 2 isotopes are bonded to a tetrahedral center, assign priority based on mass number. Okay, so again, it's based on mass number. If there are 2 or more of the same atoms bonded to a tetrahedral center, look for the first point of difference. Groups containing double or triple bonds are assigned priorities as if both atoms of a multiple bond were duplicated or triplicated. All right, so let's look at the rule. Rule 1, look at the first atoms directly attached to the chiral center and rank them according to the atomic number, okay? So the higher the atomic number, the higher the priority. Atoms with highest atomic number have the highest ranking, and the atoms with the lowest atomic number has the lowest ranking. So hydrogens are always going to have the lowest ranking because hydrogens are the smallest atomic number. Now, if you have deuterium, then that is actually ranked higher than the hydrogen. Rule 2, if a decision cannot be ranked by the first atom of the substituent, look at the second, third, and fourth until they're different. So let's look here. If I have a carbon that's on a substituent, and then this carbon's bonded to 3 hydrogens, compared to if I have a carbon, and then you have 2 hydrogens, but then the next one is a carbon, this would have higher priority, okay? Again, if you have an OH group, an oxygen and oxygen are the same. However, I go to the next atom, hydrogen is lower than a carbon, and so forth. Again, if I have a carbon and a carbon, they're the same. But if I reach out again, this is bonded to a carbon and a carbon, whereas this is bonded to a carbon and then 2 hydrogens. So this would have higher priority because 2 carbons are bigger than a hydrogen with 1 carbon. Lastly, if I have a carbon, that's the same. If I go out to this, I have a nitrogen, which is the next biggest thing. This carbon is bonded to a chlorine. Chlorine has a higher atomic number. Therefore, this would ultimately have a higher priority. All right, so rule 3, multiple bonded atoms are equivalent to the same number of single bonded atoms. So here, this carbon here would be the same thing as if I visually saw it as a carbon with an oxygen, which is, this is a carbon with oxygen and oxygen. Now this oxygen is bonded to a carbon here. And so ultimately, it is going to be the higher priority. But again, this is the same thing as saying this. All right, so let's go through these. Which one, the methyl group or the ethyl group, would take higher priority? If you said the ethyl group takes higher priority, you are absolutely correct, because the first carbon is only bonded to 3 hydrogens, which have low priority, whereas the second carbon is bonded to 2 hydrogens, but also a carbon. And so because of this extra carbon, it will have higher priority. Now, what about iodine or bromine? Well, which one has the higher molecular weight, the higher atomic number? You will know that iodine has the higher atomic number than bromine. Therefore, iodine would be the higher priority. What about hydrogen or deuterium? Now, deuterium is an isotope of hydrogen, and it is a slightly higher mass, okay? It's what we call it's heavy hydrogen. And so because of that, deuterium is going to have the higher priority. So now let's look at this next one. We have a carbon bonded to 2 hydrogens in an OH group compared to a carbon that's double bonded to an oxygen with a hydrogen. This carbon here is said to be bonded to a hydrogen, an oxygen, and a hydrogen. Whereas this carbon is considered to be bonded to an oxygen twice and then a hydrogen because of this double bond. One oxygen has a lower priority than 2 oxygens when in referencing the hydrogens that are low priority. Therefore, this would have the higher priority between the two. All right, so once you direct the lowest priority group away from you, you're able to look at the direction of 1, 2, and 3 to see whether it's clockwise or counterclockwise. If it's clockwise, R designation, counterclockwise, S designation. All right, so let's look at this. If the observer is looking, you want to make sure 4 is away from you. So 4 is in the back. If I count 1, 2, 3, 1, 2, 3, that is going right. Therefore, it's R. However, if I look and it's going 1, 2, 3, that is left. So it will be S. Again, note 4 has to be in the back. So let's determine whether these would be R or S. So first, let's number them based on priority. So which one would have higher priority in A? Which one has a higher atomic number? That would be bromine. Your next atom that would have the highest priority would be your chlorine. Now, if you look at your next ones, they're both carbons. One's a methyl carbon and then one is an ethyl carbon because ethyl carbon has 2 carbons attached to, because the ethyl carbon has a carbon that's attached to 2 hydrogens and a carbon, this would get priority 3 compared to a carbon that's attached to 3 hydrogens. Now notice that 4 is indeed in the back and you see that with the I see that with the dash. So if I'm looking at this, is it going clockwise or counterclockwise? It is going to the right, going clockwise. Therefore, this is going to be R. Now let's do it for B. Can you designate this if this is R or S? All right, now I will do it. Let's count 1, 2, 3. Notice H is not in the back. So if I know that H is not in the back, H, which is 4, is actually in the front. Therefore, if I look at it from a different angle, I will notice that while it appears to be going in the S configuration, because left is left, because H is in the front, S then would be considered technically R. Because again, your observation needs to be from the back. So that hydrogen is in the back. Okay, so if after you number them and hydrogen is in the front, then if after you number it and you determine if it's R and S, you're going to change it. Okay, so for A, hydrogen number 4, was already in the back. So once we determined it to be R, it stayed R. However, with our second one, after we numbered it, 4 was in the front, and so S turned into R. Now, if 4 is in the plane, meaning if 4 is one of these two, there's an extra step that you have to take, and we'll talk about that later. All right, so here goes some practice. I want you guys to practice R and S for these. Let's look at the first one. All right, now try the second. All right, now let's do C. Now, lastly, let's do D. I want you guys to actually write these down and submit them in the Dropbox if you're in my course. All right, so what if the fourth priority is in the plane? We're going to do what we call the switch method. So follow along with me. It does take a few steps. So in the first scenario, the 4 is in the back. So once we number them, we simply can go that 1, 2, 3 is going to the right, so this is R. In the second scenario, after we've numbered them, we see that 4 is wedged, so it's in the front. So after I go and number them 1, 2, 3, it's going right. However, I have to change it. So the answer is S. Now, what happens if it is in the plane? So if the fourth priority is in the plane, it's neither wedged nor dashed. You have to do a switch. So what you would do is you don't have to actually move the atoms. You're simply going to move the numbers. So you're going to look and see what number is in the back. Well, in this scenario, the number that's in the back is the bromine at number 1. So you're going to erase the 4 and make that 1, erase the 1 and make that a 4. Now changing them makes them actually the enantiomers of each other. And so if we change one, we have to change the other to recreate the original enantiomer. And so now I'm going to take 2 and make it 3, and 3 and make it 2. At this point, my numbers have been rearranged, so 4 is in the back. So I can simply now say 1, 2, 3, and see that it is going right. Therefore, this is R. We're going to do some more practice. If I have a carbon, excuse me. All right. So first, I'm going to number my priority. 1, 2, 3, 4. I noticed that my 4 is in the plane. So I have to do some switching around. So what is in the back? Bromine is in the back as a number 2. So I'm going to cancel my 4 and make this a 2. I'm going to cancel my 2 and make it a 4. Then I'm going to switch the other 2. Once I've made the switch, I'm going to draw my arrow. 1, 2, 3. It's going to the right, so it's R. And that's how you do it. I suggest you go to the book and do the practice problems from the chapter. All right, so how do you physically distinguish a chiral molecule from its mirror image? So the question is how can you physically distinguish enantiomers? Well, enantiomer pairs of molecules have similar physical properties. Their boiling points, their melting points, and their solubility and densities are very similar. They're often the same. However, they do differ in a way in which they interact with plane polarized light. All right, so what is plane polarized light? So ordinary light consists of electromagnetic waves, all right? They're oscillated in a wave function in an infinite number of planes at right angles to its direction of travel. So optically active property of organic compounds to rotate plane polarized light that passes through it, all right? So optically active means that the organic compound can rotate the plane polarized light as it passes through. So light passes through a polarizer, all right? So a polarizer is an instrument that has polarized light and is rotated in solution as optically active compounds. So you have laboratory, which is optically active substances that rotates a plane of polarized light, in a counterclockwise direction. And then you have dextrorotatory, which is optically active substance that rotates a plane of polarized light in a clockwise direction. So you have some substances that do it counterclockwise and other ones clockwise, all right, as it goes through the polarizer. All right, so let's show you how this works. So you have polarized light, which is your light source, and it goes through a polarizer. When it goes through a polarizer, it is able to control the light and in a sense of polarizing it. So you see how it's going in all directions, but now the light is just polarized north and south. So then as it goes through a sample container that you see here, if it rotates counterclockwise or clockwise, the light is going to move and it's going to bend. Now, as it bends and goes through, ultimately it goes through an analyzer. And there, the observer or the instrument is able to record that information. So let's look at some values. So as you see, penicillin V has a plus 233, sucralose plus 66.47, and so forth. Now, if you see things such as chloroform, you notice that it does not have any rotation. Also, as you see, acetic acid doesn't have any rotation. So only compounds that consist of chiral sensors, which are chiral, will have the optical activity. So again, only compounds that are chiral will have optical activity. All right, so again, if we have enantiomers, so you have one compound or one enantiomer that we're going to call A, and then one that's we call B. And then racemic, look at the word racemic. Racemic is when you have a mixture of a 1-to-1 ratio. So it's a 50-50 ratio. So you have the exact same amount of A as you have of B. So let's look at some of these properties. You will notice that the melting point of A and B are identical. Now, with the racemic mixture, they may actually different from A and B. All right, so when it's racemic with melting points and you have a mixture, they can be different. Now, with boiling points, you have identical B and A. A and B are identical in melting point. However, when they're mixed, they may have a different melting. They may have a different boiling point. Now, let's look at the optical rotation. So, the optical activity of A is going to be the opposite sign of B. Therefore, if A, for example, was positive 23, B would be negative 23. So the enantiomers are going to have the equal magnitude of rotation, but in the opposite direction. So one would twist it clockwise, the other one counterclockwise with the same amount of magnitude. Okay, and again, just highlighting racemic mixture means that it's a 50-50 mixture of a chiral compound. Okay, now when it's a 50-50 mixture, because it has the magnitude that is equal but in opposite directions, they actually will cancel out each other. And so the optical rotation of a racemic mixture is going to be 0. Okay, there'll be 0 degrees, and that's because they cancel out each other. So if it's plus 23 plus a minus 23, that equals 0. Okay. So let's know something. A molecule with a single tetrahedral center is a chiral compound. Okay, a molecule with a single tetrahedral center is a chiral compound. And all chiral structures may exist as a pair of enantiomers. Okay, so when you have a chiral center with a single tetrahedral center, they're going to exist as a pair of enantiomers. So you'll have one that's an R and the other will be an S. So what if you have more than one chiral center? Well, other configurational stereoisomers are possible if more than one stereogenic chiral center is present in a structure. However, we're not going to talk about that until next time. All right, so that's the end of our lecture. And next time, we're going to talk about more of the options as you increase the number of chiral centers. Until then, practice being able to identify chiral centers as R and S.